Good morning, this is your Stat Sensei, Mr. Spensei, and this is Notes on Regression. It's going to be page 317 and 318 of your note spiral. And this is off the AP exam from 1999. It's question one. Lydia and Bob were searching the internet to find information on air travel in the United States. A likely story. They found data on the number of commercial aircraft flight flying in the United States during the years 1990 to 1998. The dates were recorded as years since 1990. Thus, the year 1990 was recorded as year zero. So 1990 was recorded as year zero. This means this is 1991, 92, 93, 94, 95, 96, 97, and 98. And they already said that year zero was 90. All right. So they have the residual plot, and we see that we have a bunch of random dots. And then the next thing we see is we have a computer printout. We might as well highlight the important word. The important word that sets us off is constant. That's our slope intercept row. And of course, or I should say, you know what, instead of slope intercept, let's call it just the y-intercept row, less likely to be confusing. And the row below it is our slope row. Kind of a short printout, but it still follows the same thing. You find the constant, find the word constant, and you're good to go. You know that years happens to be our x, so that's our explanatory variable. All right. Is a line an appropriate model to use for these data? What information tells you this? Well, this is kind of trying to trick people. They want to go, oh, it's got a high R squared, and that's good. And it is good. And if I do the correlation coefficient, raise it to the half power, I get a correlation of 89%. So it's a strong linear relationship. And it's positive. Yes, it's all of those. And we know it's positive because the slope is positive. But the way we know whether or not a line is appropriate is by looking at the residual plot. So I have to go to say, hey, is the line appropriate? And the way I do that is I look at the residual plot. And remember, I want the residual plot to be random and without pattern. And I can tell you, if I put my marker here, I don't know if the next point is going to be above or below because it is completely random. So our answer is yeah, a line is appropriate. A linear model appears to be appropriate because the residual plot appears to be random and without pattern. All right, random and without pattern. Question B. Use the computer output to determine the equation of the least squares regression line. Okay, so we know that we have y hat equals 2939.93, 2939.93 plus 233.517x. Well, that's all great, but if I do that, I have to define my variables. So let's take a look at this real quickly. As a matter of fact, it says I identify all the variables used in the equation. Well, right here, we know that this is our x, so that's good because we already said that. Let's go back and look at this. Liddy and Bob were searching the internet to find information on air travel in the United States. They found that data on the number of commercial aircraft flying. So data number of commercial aircraft flying in the US during the years 1990 to 1998. So it looks like we have number of aircraft flying and years. All right. The dates recorded as years since 1990. Thus, the year 1990 was recorded as zero. They fit a least squares regression. So it looks like we have years being our X, and it looks like number of commercial aircraft. So Y hat's going to be the number of commercial aircraft. So once again, there it is written technically, or here it is written technically, just the way I wrote it there. but this should really say number of flights equals 2,939.93. That's my y-intercept. And 233.517 is my slope. And this right here is my years. So I'm going to do a little bit of highlighting real quickly. That's my y-intercept. This plus is my slope. This is my x, and this is my y. Okay? So number of flights is my y. This is my y-intercept. This is my slope. All right? So y is the number of aircraft, commercial aircraft flying, and x is the year since 1990, or number of years. Next thing, what is the value of the slope of the least squares regression line? Well, we just identified that. That's at 233.517, and it happens to be positive. As I've said before, write it as a fraction and put it over 1. So the very first thing we do is put this over 1. So remember, it's always y over x. So the number of flights over year, because flights was our y, x was our year. So on average, there's a 233.517 increase. So a couple things. First off, that's just my slope. And this is positive because my slope is positive. So the reason it's increased is because it's positive. If it had been negative, we would have wrote decrease. So in the number of flights, this is my y, for every 1 unit increase in the number of years, which is my x. And remember, we're always going to go yx, yx. All right, the next thing, what is the value of the intercept of the least squares regression line? Interpret this in context. Well, our intercept is 2,939.93. And the y-intercept always is set pretending like x is 0. So in this case, the y-intercept is 2,939.93. And what that means in year 0, which was 1990, our model predicts that there were 2,939.93 aircraft because that was our y value. All right, continuing on. That's page 317. Page 318, we have the same problem, same scenario. I'm going to go ahead and highlight the word constant so we know we have our y-intercept row. And then I'm going to highlight our slope row. It says, what is the predicted number of aircraft flying in 1992? Well, to do that, I'm going to need my regression equation. Well, my regression equation is y hat equals 2939.93 plus 233.517x. Now, when we looked at it, 1992 is shown as year 2. So we're not going to plug in 92. We're going to plug in 2 for x. So I'm going to plug in a 2 right there for x. So when we do that, 2939.93 plus 233.517 parentheses 2. And we get 3,406.94. All right. And all we did was plug in 2, and that was because that represented 1992 as year 2. Okay. Next thing. What was the actual number of aircraft flying in 1992? Wow. Well, they didn't give me that information, but I can be pretty smart because residual equals observed minus expected, or actual minus predicted. Well, we know the predicted is 3,406, And if I go to 1992, it's like, oh, it looks like 40 was my residual. So I'm going to plug in 40 for my R and 3,406 for my expected, and then I'm going to solve. So 40 equals observed minus, and instead of 3,406, I just rounded up to 3,407. And when I solve that, I add 3,407 to both sides of the equation so that I get the observed by itself. This will cross out, and 40 plus 3,407 is 3,447. So what was actual was 3,447 because there wasn't a 0.96 plane. Okay. The next thing, it says write the coefficient of determination and explain its meaning in context. Well, we'll never find the coefficient of determination, but we will find R squared. So let's look for R squared. Well, once again, they tried to trick us. They gave us two R squareds, but we will never use adjusted. So R squared is 79.3. So 79.3% of the variation in the changes in the number of commercial aircraft can be, and it should say flying, can be explained by changes in the number of years since 1990. So, number of commercial aircraft flying can be explained by changes in the number of years since 1990. And the reason I'm highlighting those like that is because this is my Y and this is my X. And of course, the 79.3% is my coefficient of determination. Okay. The next thing, write the correlation coefficient and give its meaning and context. Well, remember, correlation coefficient is a combination of slope and the square root of R squared. So the sine of the slope, and R squared. Well, what was the sine of our slope? When I look at this, it's not negative, so this is a positive slope. So we're going to have a positive square root of R squared. So I need to turn that, divide that R squared by 100. My R squared is 79.3. So 79.3 divided by 100 is 0.793. So positive square root of 0.793. When I do that, I'll just raise it to the half power, I get 0.8905. So 0.8905, there is a strong, and we'll talk about strong in just a moment. We know the positive came from the slope. A strong positive linear relationship between the number of years since 1990 and the number of commercial aircraft flying. And by the way, I accidentally switched these. This is my Y and this is my X. Normally we want Y before X. So I should have fixed this. This is my X and this is my Y. Okay? And you can see right there that we just took the square root of our coefficient of determination and calculated the 0.8905. So strong, where did that come from? If R is greater than 0.75, it's strong. 0.4 less than R less than 0.75, moderately strong. Running out of room. Moderately strong. And finally, if R is less than 0.4, it's weak. Okay, and so ours is we have an 89, that's definitely greater than 75, so this is definitely strong. It says calculate and explain what S is in the context of the problem. Well, S I'm just looking for a lonely S up there. When I hunt around, S is 33.43. And remember, that's the standard deviation of the residuals. So S is 33.43 and is the standard deviation of the residuals and measures the amount of variation in the number of commercial aircraft flying in a given year. So, number of commercial aircraft, there's my Y, and here's my X. So once again, we're going back to that Y and X. I apologize that the one of them is not fixed. All right, the one thing we really haven't talked about and wasn't tested about, it says identify the standard error of the coefficient in context. So standard error, and really they wanted the standard error of the slope. That's another word of saying we're looking for SB. Well, remember this is B and this is SB. So standard error is 0.4316. So the standard error of the slope is 0.4316. And because the slope is estimated from the sample, other samples are likely to have different slopes. So what that is trying to say is you might have a slope that like that might be yours, but someone else's sample might look like this or like this. So the slopes could vary. So the standard error of the slope quantifies the amount of variation in the sample slopes that could be expected from different samples. Because everybody has a different sample, everyone could end up with different slopes. And this just tells you how much that slope could vary. And it looks like it could vary by about 4 airplanes per year. All right. I hope this helped. Appreciate you watching and appreciate this year. Thank you.